Turn it on.
Well, hello, everyone. Is anybody here for some science? And you thought you just came for beer. If you don't know what's going on, you are a Wavelength Brewing Company, and we love science just as much as we love beer. So part of our Friday night series is to bring in some fantastic, brilliant minds to let you leave a little smarter. Recently, they announced they are adding 4 elements to the periodic table. And that astounded me. And when I tried to read and pronounce them, it astounded me even more because I couldn't do it. So I call my good friend Shane up, and I said, Shane, please come and let us know not only what is up with these new elements, but what is up with the periodic table, why is it awesome, and what is it all about? So without any further ado, please welcome Professor Shane Haggard.
Oh my God. Well, thank you, Hans, for that very nice introduction. Don't know if I can follow that now, actually. But yes, my name is Shane Haggard. I am a chemistry professor down at San Diego City College. And we are going to talk about the periodic table tonight. For me, it's my best friend as a chemist. I think it's amazing. I actually wore the correct shirt for the evening, if you notice. I only wear this shirt periodically, and periodically means I only wear it when I talk about the periodic table. So this is perfect, right? I'm wearing periodic table shirt, periodic table. And when you look at the periodic table, I know what people think sometimes, because I teach an introduction class every once in a while. And the students look at that and going, oh my God, what are we supposed to do with this? It's so confusing. There's all these letters, there's all these names, there's all these numbers. Why is it arranged in that weird way? What is all this down here? Why is it iron has a symbol of Fe? You know, what is going on? You know, sodium is Na. What were people thinking? Were they doing this just to confuse us? And actually, the periodic table is built this way for a lot of different reasons. Partly because of atomic structure, the way atoms are actually put together. But it's named the periodic table because it has something to do with periodicity. In other words, a repeating pattern. All right, and the very first person to actually look at the periodic table and actually arrange the periodic table was a Russian chemist by the name of Dmitri Mendeleev. Now, Mr. Mendeleev lived from 1834 to 1907, and he put this periodic table together in 1869. Now, what he did was he was studying the different elements, and scientists at the time knew masses of elements. They knew that sodium had a mass of 23, and chlorine was 35 and so forth. They knew the masses of elements. And what Mendeleev did was he arranged the elements in increasing mass. Now, something interesting about Mr. Mendeleev was he did not believe in the noble gases. So helium, neon, argon, krypton, he didn't believe that they existed. And he also didn't believe that hydrogen was the lightest element. He said that there were actually lighter elements. So he had a few little quirks about him. But what he noticed and what he actually studied was there was a repeating pattern. All right? When you arrange the elements in the periodic table according to increase in mass, there's a repeatability in certain chemical and physical traits. And what he did was he started grouping those elements together that had similar chemical and physical traits into families. And he came up with the world's first periodic table. And that's what it looks like. All right, a little different than what we look at today, definitely. But there are some similarities to our modern periodic table. Instead of the periodic table that we are used to seeing going from left to right, all right, he arranged it up and down. So if you notice, here's boron, carbon, nitrogen, oxygen, and fluorine, which is boron, carbon, oxygen, nitrogen, and fluorine here. So they are still arranged. So his families go across. So here's boron, aluminum, whole, carbon, silicon, whole, tin. So looking down, they go this way. So every group going up and down is a family that have similar properties. So he arranged the periodic table this way. He's got to looking at these different trends and these different properties. And he arranged things according to things like reactivity. All right. And he made some pretty bold predictions because of what he was noticing. Like I said, if you look here in his periodic table, he's got some question marks. All right. And he predicted based on the repeatability of some of these properties, that there should be elements there, just not holes, that have not been found yet. In fact, he predicted 8 elements, all right, and 4 of which were actually found in his lifetime and actually confirmed that that was actually true. 2 in particular, which I like to point out, are what's called Eka aluminum and Eka silicon. Eka means below. Now, I don't understand why he said below when his periodic table went to the right. I guess his world was kind of sideways or dyslexic or something. But anyway, he said below. And Eka aluminum turned out to be gallium. And he predicted its weight would be about 68, 69.7. That's pretty good for a guess. Predicted the density and all these. He predicted its reactability. All right, if you react it with a chlorine, this is what you're going to get. If you react it with oxygen, that's what you're going to get. He actually predicted the one under silicon, which is called germanium, which was discovered a little bit later. So like I said, gallium was discovered in 1875 and germanium in 1886. This led to scientists going, hey, his predictions are true. There are holes there that we haven't found yet. So there really became a mad rush in the late 1800s, early 1900s to find these missing elements and to figure out where they are and what they are. And if you could figure them out, you probably got some pretty good recognition here. Some of the other ones that he predicted were things like ekaboron, which is scandium, ekamanganese, which is actually technetium, not technetium, technetium. I can never say that word for some reason. And that was actually the first man-made element. It does not occur in nature. But he predicted there should be something there. And it wasn't until it was made in the early 1900s, that is actually 1937 to be exact, that it actually did fill in that hole. Now you're probably asking me, well, how did they actually do some of these tests? How did they figure out what reactivity is? Well, what I wanted to do tonight to show you is actually do one of the experiments that Mendeleev did. So you guys in the front are in the splash zone. All right. Now, when you talk about reactivity, you talk about reactivity with things reacting with certain substances like water or acid or air. All right. So what I got here is just some water. Plain old dihydrogen monoxide. It's an awesome substance. I actually did a whole talk about water once. All right.
Yeah.
Huh?
Do it again sometime.
I will. If Hans invites me back, I'll do it again. All right, so this is just plain old water. And what we're going to look at, I'm going to back up a couple of slides if you guys don't mind. I do this all the time to my students. It drives them nuts. I'll go back here to the periodic table. And what I'm going to be looking at is this first group. All right? This group is called the alkali metals. When these react with water, they make a basic solution, something that has basic properties. And what I'm going to look at is the first 3, lithium, sodium, and potassium, because I can't get my hands on rubidium, cesium, and francium. They just won't let me have that. I'm sad about this, but I think they've learned their lesson with all the burn marks in the ceiling at the classrooms that they should not let me play with things that are very reactive. So I'm going to start off with a little lithium. All right. Now, these are so reactive that they're actually stored under mineral oil because they will actually react with the oxygen and the water and the air. So lithium, unfortunately you can't see it, is a shiny kind of metal. I'm going to wipe off some of the oil. And you're going to notice what happens when I throw it in water.
Oh my God.
Well, you could do a little bit more. I mean, come on. All right, so you notice that it's a little bit of smoke coming off. There's a little bit of sizzling. It's a little reactive with water. All right, the smoke that's actually coming off is hydrogen gas. If I had a candle, I could light that, and it would be like a little fireball. Notice I'm not doing that. And it's turning the water basic. If I had an indicator that would turn colors when something is basic, it would actually turn that basic. And it just kind of sizzles and just kind of, dancing around on the top. Oh, it's not so much fun. All right, so, you can imagine Mendeleev sitting in his lab and doing this. Oh, let's see what lithium does. Throws it in there, kind of watches it for a little bit. So then we're going to go to sodium. Now, sodium is the first component for salt. sodium chloride. Let's see. Let's get a nice piece of sodium here. The sodium, I'm not going, ooh, that's a huge piece. I'm not sure I want that piece. Oh, maybe I do. All right, I'm going to keep a couple of pieces up here, so after the talk, if you want to actually come up and see what some of these look like in real life, you can. All right. All right, so this is sodium. Now, notice sodium is one down from lithium. All right. Let's see if something else happens. All right, now notice that this one's a little more vigorous. Sodium is a little more reactive than lithium. Okay? So you're talking about reactivities here. So we're going down the periodic table. You can only Mendeleev. He's got a little bit of sodium, cuts it off, throws it into some water. You know, fizzle, spark, fire, boom. All right? So you notice that lithium, kind of reactive. Sodium, a lot more reactive. What's next down on the periodic table? Potassium. Well, I've got some potassium. Yes, this sounds safe. And I'm actually going to try to cut this in half if I can. Oh, it does cut in half very easily. So this is potassium. Okay, come on, be a little more exciting than that. Really, potassium? Let's try another piece. Science never always works like you plan. All right, a little more reactive. Hopefully we get something a little more exciting with this. Well, the reality is potassium is supposed to be more reactive, but apparently I had a nice big piece of sodium when I threw in there. But this is what Mendeleev did, all right, was he actually took these elements and reacted them. The group 2 guys, the calcium, magnesium, beryllium, and all these guys, they don't react with water. They react with acid, though, particularly hydrochloric acid, all right? So the different parts of the periodic table react differently, and this is the things that Mendeleev studied when he put the periodic table together. All right, so with that idea in mind, let's talk a little bit more about the periodic table and why it is like it is. So we understand now the periodic table is arranged because of periodic trends, things repeating patterns, reactivity. All these up here, as you're going to look at, as you're going to see if you come up here, they're all metals. They're all very soft. All right. I actually just have a pair of tweezers here. I cut those into little pieces. They're very soft. They're actually very shiny when you cut them. All right. The other side of the periodic table are all gases. There's some noble gases that are non-reactive. There's the halogens that have like chlorine and fluorine and bromine that are very reactive gases. So the periodic table is put together because of the repeating patterns. Now the thing is that always gets my students is, why in the world do we do the names that we do on the periodic table? Has anybody ever wondered why sodium is called Na? Nah. That's usually the joke where it goes, is nah, no. All right. Well, sodium's name actually comes from the word natrium, N-A-T-R-I-U-M, which is Latin. And sodium is the first component in sodium chloride, which is salt. Now, salt is a very valuable commodity. Extremely valuable commodity, especially in ancient times. In fact, Roman soldiers were paid with little salt coins, basically little salt tablets, called salarium, S-A-L-A-R-I-U-M, which is where our word salary comes from. We get paid with salt. All right. The next one over is germanium. All right, GE. This is one of the ones that Mendeleev predicted. Now, germanium comes from the Latin word for Germany because germanium was actually discovered in Germany. All right, so that's where its name comes from. Now, uniquely, its original name was not germanium. It was neptunium. Because the same year germanium was discovered, we discovered the planet Neptune, which is kind of cool. Unfortunately, another element that had been discovered the same year had already been proposed to have that name, and because of all the arguing and infighting about it, neither one of them got named Neptunium. Something else down the road got named Neptunium. All right. The next one there is chlorine. All right. Chlorine is a nice mustard yellow looking gas. It actually comes from the Greek from yellow-green. So this is where its name comes from. So the names on the periodic table actually do have meaning. They come from either ancient Latin, ancient Greece. Different parts give us some of the names, all right? They're not just always so we can trick students or make your lives miserable by knowing that iron comes from ferrum, which is why it's Fe, and tungsten comes from the Swedish for heavy metal, which was wolfram, or wolfram, depending on how you want to say it. Now, these are all naturally made elements. These have been found in nature and so forth. But because of the periodic table, people predicted that there would be ways to actually make more elements. In fact, technetium, one of the elements that Mendeleev predicted, is a man-made element. It's the lightest man-made element. It's like element 43. We actually use this in like medical technology. It's really used in like CAT scans and MRIs. But the person who was really instrumental in really driving the periodic table and driving us to look for new elements was Glenn Seaborg, all right? 1912 to 1999, and he discovered Seaborgium, all right, in 1974. He is also credited for the following elements: plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendeleevum, and nobelium, along with seaborgium. He actually created 10 elements on the periodic table, which all fit down here on this bottom row. All right? My little shirt here is a little old. These have been named, all right? Now, when you're talking about naming new elements, the discoverer gets to name them. All right? Whoever discovered gets to name them. So, plutonium, americium, curium. All right, plutonium after Pluto. That's the same year Pluto was discovered. American, because we found it in America. Curium after Madame Curie. Einsteinium for Einstein. Berkelium for Berkeley. Now, one of the biggest controversies we had was the fact that Seaborgium, number 106, was proposed to be named after Mr. Seaborg himself. But he was still alive. He didn't die until 1999. And there were lots of people in the scientific community who said, nope, you do not name elements after living people. Seaborgium was actually, it went for several years. I think it was like the early 80s before 106 was actually named as Seaborgium, because there was so much infighting about the name and the fact that he was still alive. It's just something you don't do, is name elements after them, after people. However, that's going to change when I make my element. It's going to be Shanium. That's all it is to it. All right. Now, like I said, making new elements is something we can predict because of the periodic table, predictability. And this is an old periodic table. Here's some of those ones that have been filled in. All right, here's Seaborgium, Bohrium, Hassium. There's Mendeleeum, Curium, Berkelium. All right. Everything past 92. 92 is the last naturally occurring element on the periodic table, uranium. The rest of these are all man-made, including number 43. Now, one of the big driving forces was to complete the periodic table. All right, this is an old periodic table. These guys had already been named, but we wanted to finish out row 7. And that's what we have finally done. We have finally finished the periodic table. Now, this has been going on for a long time. We've actually been discovering these elements and confirming them since around 1999, all right? So we've been looking at this for about 15 to 16 years. And I really think it's exciting because I remember in 2001, when I was a student and was going back to school, element 115 and 113 had just been confirmed in 2001. And I remember this because it was a big deal in my science classes that we have now created 113 and 115, which was like almost impossible to do, all right? But now we've got 113 and 115, 117 and 118. They have been confirmed at the end of last year, December 2015. They have been confirmed to be real. All right, and to confirm this, the researching lab that creates them gives their work to other research labs, and those research labs then try to reproduce the results. So they have been reproduced, and now it's just a matter of naming them, and we should have them named by the end of the year. But at the end of last year, 114 and 116, Fleverum and Livermorium were actually confirmed, and were actually named, all right? Now, Fleverum comes from the Flever Laboratory of Nuclear Reactions, the Joint Institute of Nuclear Research in Russia. All right. It was actually discovered in 1989, and it just got named last year, so it takes a while for this actually to go through. When they actually discovered it, they discovered about 90 atoms of it. 90 atoms, that's it. And they only lasted for about 2.2 to 2.9 seconds. For a heavy isotope like this, or a heavy radioactive element, that's a long time. That's a lifetime, all right? And to get 90 of them is a pretty big deal. Unlike livermorium, which was actually discovered by the Lawrence Livermore Research Lab here in California, they were discovered in 2000, and this was with a joint research with Russia. And they only made about 6 to 8 of these atoms, and they only lasted for about 60 microseconds. Not a lot of time, but they have been confirmed, which is a really big deal that we're actually finishing out the periodic table. The last 4, all right, which is 13, 15, 17, and 18. 13 was done by Japan, all right? They're the ones that's going to get to name it. And the other 3 were joint between the US and Russia, so we get to name these as well. They're supposed to be named at the end of the year. Now, this guy right here lasted about 19 seconds. 220 milliseconds, 5.1 milliseconds, 0.89 milliseconds. You know, we're not talking about these lasting a long time and there being a lot of them. So the question is always asked, my students always ask me, like, why do we do this? Why are we so concerned about these elements that we can't do anything with? Well, we can predict their properties. All right, we can predict because in a certain family they're going to have certain properties. But there's a whole goal in science, in chemistry and physics, to create what is known as a heavy, stable atom. And the belief is when you hit 126, it will be a stable, heavy atom. And if that actually occurs, it will actually change the way we look at chemistry and physics. All right, right now all we're looking at are radioactive and they fall apart. When we discovered technetium, which is a very light atom, it revolutionized the way we do X-rays and the way we do radiology, because that's what we use now to do an MRI and to do a CAT scan. So we're looking at maybe in the future having a lot of unique scientific discoveries if we can create this heavy, stable atom that will still fall within the periodic table somewhere. I hope you learned something fun tonight, and I hope you enjoyed the demonstration. And thank you very much. Have a good evening.
Yeah, just want to tell you about next weekend. We're actually celebrating our 1-year anniversary. Can you believe we've been doing this for a year? It's just crazy. A whole year of beer and science has just flown by, and we can't wait for number 2. So we'd like to invite you all. It'll be on Sunday. And we'll be releasing an anniversary beer, a Belgian IPA that is quite delicious. But so one more time, everyone, let's give Shane a big hand and say thank you very much. So it is a beautiful night out there. Give us about 20 minutes or so, and we will take some telescopes out and show you what we can see. All right? Cheers.